All right. Welcome to the RL Theory Seminars, everyone. The slides for the talk are shared in the chat. They're pinned there. So I'm just going to explain how these seminars work. So the presenter today is Matthew, and Matthew will be giving a presentation for about 50 minutes. That's 50 minutes. During the presentation, feel free to unmute and ask any questions. Or if you want to ask your questions in the chat, you can do so as well. And then I'll unmute and just ask them for you. If you have longer questions, there's going to be a Q&A at the end, which you can use to ask your longer questions. And today, my co-host will be Zurek, who will be stimulating Matthew with lots of technical questions. And otherwise, I'm just going to give a quick bio of Matthew. So Matthew is a PhD student in the computer science department at the University of Wisconsin-Madison. He's advised by Yudong Chen, and his research interests span machine learning, optimization, and high-dimensional statistics, and particularly the theory of reinforcement learning, which he'll be talking about today. So go ahead, Matthew.
Thanks. Yep. And yeah, thanks to the organizers for inviting me. So yeah, I'll be presenting my joint work with Yudong, which is titled Span-Based Optimal Sample Complexity for Weakly Communicating in General Average Reward MDPs. Okay, so yeah, my motivation here will sort of be about not exactly the average reward setting, but a bit more about the discounted setting. So especially like in practice, discounted MDPs are ubiquitous, and sort of problems are modeled as discounted MDPs all the time. And so sometimes this discount factor that you use is an actual fundamental part of the problem. Maybe it's like has some interpretation, like you're talking about economic problem and it has an interpretation in terms of the interest rate or the inflation or something, or maybe the problem just has a small horizon and you're fine with sort of discounting and not worrying about long term. But in many situations, you care about the long-term performance, like an infinite horizon, and gamma is more of just a tuning parameter, and you're just going to increase it until you have a sufficiently non-myopic policy. And so I guess I would argue that when you're doing that, you're really sort of caring about the average reward setting, even if you're using a discounted algorithm or model to solve it. And so that sort of motivates some of the main questions that I want to sort of explore during this talk, which is, first of all, how can we solve average reward RL problems with discounted algorithms, which is the only algorithm that I'm going to be talking about today. And yeah, what is the right choice of gamma to do so? And also, how does the problem complexity of discounted reinforcement learning, how does it depend on gamma, especially for a fixed instance? So right from this perspective that we have a fixed instance and we're just going to tune gamma, how does the complexity then scale with gamma for this fixed instance? In particular, does it have a cubic, as sort of we're familiar with, like the standard minimax sample complexity for discounted MDPs, or does it have a quadratic dependence on the effective horizon? So yeah, for the outline, so first I'm going to give some background and define a lot of things for both the average reward and discounted settings, so I apologize for all the notation and definitions. And then yeah, I'll give some results and then some proof sketches for weakly communicating MDPs, and I'll define weakly communicating MDPs in a second. And then I'll give some motivation and results for general MDPs, and then I'll try and give some really brief proof sketches for some of our results in that setting. So first I'll start with the background. So as many of you are probably aware, the most common model in reinforcement learning is of the Markov decision process. So we're going to assume that we have finite state interaction spaces, script S and script A, and they have cardinalities S and A, and yeah, transition kernel P, and a known reward function R, which is a function of state interaction, and we're going to assume that it's bounded between 0 and 1. And then a policy, which I'll be using pi exclusively to denote policies, is a mapping from states to a distribution over actions. And so yeah, a policy plus an MDP induce a Markov chain with a transition matrix P subscript pi is the notation I'm going to be using. And so when you also sort of add affix a starting state S0, then that induces a trajectory over or a distribution over trajectories. So you have the states as actions A and rewards R, which is just the deterministic function of the states and actions. And I'm going to be using this notation here to denote that the expectation with respect to that distribution. And so now an important definition for the average reward setting, where sort of structural properties of the MDPs play a much larger role. So I'm going to define a weakly communicating MDP. And so this is an MDP, which is the union of sort of two sets of states. So one, a sub-MDP where all states are reachable from each other by some policy. And then two, a set of states which are transient under all policies. So you'll always end up in that sub-MDP, which is communicating, where all the states are reachable. So now I'll talk about sort of the definitions of optimal policies in discounted and average reward settings. So in the discounted setting, here's a definition for the discounted value function of a particular policy pi starting in a state S. So it's the following sort of discounted sum of rewards. And the optimal policy, which I'll be noting as pi gamma star, just to make the dependence on gamma explicit, is defined in the following way. It optimizes this value function, and it does that across all states simultaneously. And so for the average reward setting, we'll be focusing on the gain of a policy. So that's this rho pi of S. And so that is the following limit. So it's basically, instead of discounting, you take an average. So yeah, this is the limit as t goes to infinity of the average of the rewards in the first t time steps. And so even though this gain, and so we can define the optimal gain as sort of similarly taking the supremum over all policies to say the optimal gain that you could, that any policy could achieve starting in that state. And so yeah, even though I've defined this, in general, it should depend on the starting state. For weakly communicating MDPs, this is constant independent of the starting state. And so I've also wanted to define Blackwell optimal policies. So I'm going to use pi star, so no subscript of gamma for that. And so this policy and such a policy always exists. At least one such policy always exists, and it's gamma discount optimal for all sufficiently large gamma. And as a consequence of that, it will achieve the optimal gain. So its gain is equal to the rho star. So yeah, our goal will be to learn optimal policies both in the average reward and discounted settings. So we're going to assume that we have access to a generative model which can provide us n samples from each state action pair from that distribution of the next state, from each such next state distribution. And so like the main metric that we're going to be concerned with is the sample complexity, which is the number of samples n needed per state action pair. And so in the average reward setting, we want to learn epsilon optimal policy. So that's sort of in terms of gain optimality, meaning it's within epsilon of the optimal gain. And then for the discounted setting, we're concerned with the discounted value function. So we want to learn policies that are delta suboptimal with respect to that discounted value function. So now I want to discuss some complexity parameters for average reward MDPs. So one parameter is the diameter D. So this is the maximum amount of time for a policy to reach one state from another. So I guess as I've written it here, if you start in state S1 and then eta S2 is the hitting time for state S2, this is the expected amount of time required to reach state S2 from S1. And then this is the infimum over all policy. So you can choose any policy to try to reach state S2 from S1. And diameter is the maximum over all pairs of states, how long that takes. Another complexity parameter is a uniform mixing time, tau unif. So what I've written here is just the supremum over all policies of their mixing times. So how long they take to converge to a stationary distribution. And so, yeah, in general, there's no relationship between these two complexity parameters. So for example, the diameter could be infinite for non-communicating MDPs. So if there exists any transient state, then you can't reach that transient state So such an MDP would have infinite diameter. And then the uniform mixing time can also be infinite if, for example, your MDP has any periodic policy.
Sorry, can I like a quick clarifying question here? You said that your definition of communicating MDPs can actually include transient states. And those need to be transient under all policies.
Oh, so that's for weakly communicating.
Oh, I see. Okay. Right.
So yeah, the diameter is finite if you're communicating. But yeah, we're going to talk about results which hold for weakly communicating, which is strictly more general.
Right. Yeah, I guess you need to like restrict the scope of that max to be within the sub MDP.
Yeah. Can I also ask a related question?
Yeah.
Feel free to say that like we answered later. So is there some other type of MDPs that are not weakly communicating finite state space? How would that look like?
Yeah, so like I said, yeah, I have some results for general MDPs. So I guess we'll look at some examples of those. But I guess,
okay.
Yeah, like you could have two different communicating classes is a simple intuition. So
okay,
in class
if there is a single communicating class, then is there another example where like the states are not like in the complement of the communicating class, the states are not transient under all policies, but they are transient under some policies only?
Okay, sorry, what's your question?
So if I say that like let's only have one communicating class in the MDP, that's what we know about. The complementary set of states, is it necessarily transient under all policies? We can postpone.
Sorry, yeah, maybe I'll need some more time to think about that.
Yeah. It's not super important for this talk, but like just curious.
I haven't heard of classes which are more general than weakly communicating, but which are not just arbitrary.
Yeah, somehow that's what I'm wondering about. Yeah. Okay.
Yeah,
good.
I haven't heard of any between those two.
Oh, okay.
So yeah, now I'll work towards defining the last complexity parameter that we're interested in. So that's the bias function of a policy pi. And so that's this h pi of s. And so it's the following Cesaro limit. And if the policy is aperiodic, then you can replace this Cesaro limit with just the regular limit. But so it's the following sum. So compared to the average, compared to the gain, there's no averaging. So this is, if you start in state S, sort of how much, so yeah, how valuable is it to start in state S as opposed to sort of an average state? So if you start in state S, sort of how much reward do you get before you sort of converge to the long-term average reward? So there is an optimal bias, which I'm just going to be defining as the bias of the Blackwell optimal policy. And so even if the Blackwell optimal policies, if they're multiple, if they're non-unique, this optimal bias is well-defined and it is unique. And so finally, the final complexity parameter is this optimal policy span, which is the span of this bias function. And so the span of this bias function is its largest entry minus its smallest entry. So yeah, there's some sort of known relationships. So even though the mixing time and the diameter are not necessarily comparable, the span is sort of up to constant factors better than both. So it's always smaller than the diameter, and it's up to a constant smaller than the uniform mixing time. And also it's always finite in contrast to the other two parameters. And yeah, for this work, like for convenience in stating bounds, we're just going to assume that h is at least 1. Otherwise, we'd have to probably replace h with like max h and 1 everywhere. So yeah, now I'll talk about our results for weakly communicating MDPs. So suppose we have a weakly communicating MDP, then And this theorem is for the average reward setting. So this is sort of our main theorem about the average reward setting. So then there exists an algorithm such that for any delta epsilon, where delta is our failure probability, epsilon is our target accuracy. If we use the following number of samples, which, ignoring these log factors, scales like h, the optimal bias span over epsilon squared, with probability least 1 minus delta, it returns a policy pi hat, which is epsilon optimal for the average reward criterion. And so yeah, this implies sort of optimal bounds, but based off of the relationships that I just told you in terms of the relationship between diameter, mixing time, and span. This bound implies the optimal bounds in terms of those parameters, and it matches sort of the lower bounds, which follow from lower bounds that are in terms of the diameter and the mixing time from prior work.
So, sorry, a question here. So, I guess there is a bit of a mismatch between how your upper bound and the lower bounds are stated, no? Because in your sampling model, you say that you take n samples from each state action pair, right? And the lower bounds are stated in terms of total number of samples taken, no? Am I getting this wrong? All right.
I guess those lower bound, I mean, I have to think if they're...
Because there's an essay in those lower bounds, and those, those are not showing up in your upper bound.
I see the n here is per... I guess, is your question like, why is there not an SA right here?
Yeah, right.
Oh yeah, so this n is like per state action. So the total sample complexity is... Sorry, yeah, I guess this is confusing, yeah. Here I multiplied by SA, but here I didn't. Yeah, the total sample complexity is SAH over epsilon squared. So n is just per state action pair.
Right. Okay. Gotcha. Thank you.
So yeah, the algorithm, and like the only algorithm that I'm going to be talking about today is the reduction to the discounted MDP. So yeah, for each state action pair, SA will collect n samples from our generative model. We'll form an empirical MDP, which just counts sort of how many times we observe each transition from our data set. And then we'll set the discount factor in the following way. So yeah, we'll set it such that the effective horizon is on the order of span over epsilon. And then we'll just find the policy pi hat, which is optimal for this empirical MDP. And then, yeah, one issue which I won't really be discussing very much further, but it's sort of necessary actually to use reward perturbation for technical reasons related to the sample size barrier, which has appeared in some previous work. And yes, I'll say a little bit more about that, but not too much. And it doesn't really change anything, so I won't really be talking about reward perturbation all the time for simplicity. But yeah, what you actually need to do is perturb this reward vector by a very small amount for technical reasons. So yeah, given the reduction that I just mentioned to you, the main theorem I just showed you is actually a corollary of our main theorem on weakly communicating discounted MDPs. And so that main theorem is the following result. So again, yeah, assuming that the MDP is weakly communicating, and also assuming that the effective horizon, 1 over 1 minus gamma, is larger than the span, and also assuming that the desired error tolerance is not too large, then the following number of samples, n per state action pair, is sufficient to find an epsilon optimal policy for the discounted criterion. So yeah, this is sort of shaving off a factor of h. It's replacing a factor of effective horizon with a factor of h, compared to the sort of standard minimax sample complexity for discounted MDPs. So in the opposite case, when actually the span is larger than the effective horizon, you can sort of think of this as MDP is effectively being truncated before this long run behavior kicks in. And so that standard optimal complexity, which has a effective horizon cube dependence, is optimal. And yeah, when I say horizon, I'm talking about this effective horizon here, and H is the span. So yes, apologies that this is a bit confusing. And so again, this result here for the complexity of discount MDPs matches lower bounds, which follow as corollaries from the relationships between the different complexity parameters for average reward MDP. So there's already an existing lower bound in terms of the uniform mixing time.
Sorry, I have a question on that side as well. So that uniform mixing time, is that not an upper bound on H?
It is. So for the hard instances, they're equal.
Right, yeah. So the way that is proved is by constructing the hard MDP under which every policy mix is super slow, including the optimal policy, I suppose.
Yeah.
Right. Okay. Yeah, that makes sense.
Cool. So I guess, now I'll start to talk. So hopefully, I've sort of briefly talked about my main theorem, but hopefully we'll gain a lot more intuition about it as I talk about the proof sketch. And in general, one of my goals for this talk, I guess, when studying the generator setting, even if, your main goals in reinforcement learning are maybe to learn online from data, or if you're more interested in that problem, studying this setting where we have access to a generator can be sort of really helpful for understanding different theoretical tools that would be useful in other settings in reinforcement learning. So my goal is definitely to spend a lot of time talking about how to get this optimal complexity for how to shave off this factor and get the optimal sample complexity for this problem under these additional assumptions. So for the proof sketches for weakly commuting MDPs, so first I'll just describe sort of how the reduction step works. Then I'll talk about sort of how to develop improved variance bounds. So a lot of the proof centers around obtaining better bounds for certain instance-dependent variance parameters that appear in the analysis of the discounted MDP. And then I'll talk about some sort of technical issues related to improving those instance-dependent variance parameter bounds. So first, to approximate average reward MDPs by discounted MDPs. So here are the following results that sort of underpin the average discounted reduction. And so you can think of these results, which appeared in prior work, as sort of non-asymptotic versions of the following Lorentz series expansion. You can expand the discounted value function here as sort of a polynomial in effective horizon and 1 over effective horizon terms. So the leading term is effective horizon times the gain. Then the next term in the series is just the span, or sorry, it's just the bias. And then you have a term which goes to 0 as your discount factor increases towards 1. And so the following bounds, especially this one here, is sort of like a non-asymptotic version of that the discounted value function is well approximated by effective horizon times the gain up to an error of span of the bias function. And then here's another sort of result which holds for more general policies, but which has sort of similar consequences. And so just directly, if you combine these two bounds, then you can show that if you have a policy pi, which is delta optimal for the discounted MDP, then you have the following level of suboptimality for the average reward MDP. So if you find a policy pi, which has a suboptimality, which is on the same order as the approximation error that you have, and then you set the effective horizon to cancel out that approximation error, then you can get an epsilon optimal policy for the average reward setting. So now I'm going to discuss sort of why previous results obtained suboptimal sample complexities for the average reward problem, even when using a reduction from the discounted setting, or from the average reward setting to the discounted setting. And so again, that's because, I guess, yeah, the main reason is that they're using, so in particular, I'm talking about this paper by Wing et al. From 2020. And what they do is they sort of first describe the reduction that I just showed you on the last slide, but then they just plug their reduction into the minimax optimal sample complexity, the sort of standard one for discount MDPs, which has this effective horizon cubed dependence in the sample complexity. And so again, yeah, if we plug in the parameters that we just sort of derived for how to set the the desired error delta, and also for the required effective horizon. So if we just directly plug those into the sort of the known minimax optimal sample complexity bound, sort of we have the following. So yeah, we have a 1/h² from the fact that we have a really low desired, like we have a really low level of accuracy in a relative sense, like h is pretty large. So that sort of helps us, but then we're hurt by the fact that we have a really large horizon. And in particular, that horizon term, that horizon cube term, gives us this dependence on epsilon cubed, as opposed to the optimal dependence on epsilon squared. And then, yeah, I'll just mention one more time about this sample size barrier type of issue and why we're concerned about we need to use reward perturbation for technical reasons. So yeah, it's the fact that sort of we're solving these MDPs to a low level of accuracy, which is a tricky regime for like technical statistical reasons. And so that's why we're concerned about reward perturbation, is that, yeah, this delta is relatively large. Like this isn't like O of 1 or like, I guess, inverse in the effective horizon, but it's rather large. So I guess here's just sort of oh yeah, do you have a question?
Maybe it's clarification, but maybe this slide is exactly going to do the same thing. So previously you had this slide on which was saying mean result for discounted weakly communicating MDP. So it's basically the improvement is coming from an improved understanding of what happens to discounted MDPs, ironically, but in weakly communicating MDPs, right? That you have these two parameters, you have the gamma, and you also have the span. The span comes from the average reward view, which is in that moment not really needed or like per se, like it's not obvious that it should be useful, but it turns out to be extremely useful and it gives you the right quantities. Is that correct?
Yeah, that's exactly sort of that's exactly what I wanted to say here. And you
oh,
said,
sorry. Yeah.
No,
okay.
that's fine.
Okay. All right.
Okay. That's great. Yeah, that's exactly what I want to say. And actually, I want to sort of, like, as you said, right? Yeah. So that's exactly what's happening. We can replace, right, instead of having an h over epsilon, which came from the effective horizon term, we can replace one of those terms with just a span term. And so yeah, it seems like it's not obvious why that would be, like, yeah, like you said, sort of it seems like it just works, and we shave off this factor of epsilon, and that's great. We get the optimal bound. So yeah, my goal is in the next few slides to like help give you some intuition for why actually this makes sense. And it's related to what I've been mentioning before about if we think about a fixed instance and increase gamma for that instance, you actually sort of get a different sort of scaling with the effective horizon. And that's what I'm about to talk about. But so yeah, basically, just to make the point that I want to make on this slide, yeah, right. If we had this improved discount MDP sample complexity that I told you before we do have, then yeah, we plug that in, right? We shave off this factor of 1 over epsilon, because crucially, yeah, this improved discounted MDP complexity scales with the effective horizon squared, and you have an extra sort of h term as capturing some sort of intrinsic variance compared to the previous minimax complexity for discount MDPs. And so yeah, the goal is achieving this quadratic dependence on the effective horizon. And so now I want to try to like give you some intuition for why we might expect a quadratic dependence on the effective horizon, at least for weakly communicating MDPs. for now. So consider this following MDP, which is obviously, you know, they're MDPs which are different than this one. But so yeah, consider the following sort of cyclical MDP. So we start in this, assuming that we start in this state on the left, and you know, we bounce around stochastically here, collect some rewards, and we end back here at the beginning after 5 steps. Every single time, every multiple of 5 time steps will end up back here. So if we think about this instance, and we think about the task of estimating the total reward in, you know, for a policy which, you know, undergoes these transitions. So estimating the total reward for horizon T is a multiple of 5, so that we'll always end up back at this state on the left when we're done. So if we estimate the total reward that this policy collects up to error epsilon over 2, that's equivalent to the task of estimating the total reward for double the horizon to also double the amount of error, right? Like if we had an estimate for this first problem, we would just double it, and we'd have an estimate for the second problem. If we had an estimate that solved this, that had the second guarantee, we would have it, and we would have one satisfying this first bound. And so, right, if we believe that the sample complexity depends on, you know, the error squared, or 1 over the error squared, then it should also depend on the horizon squared, since these are sort of equivalent, for at least for examples like the one I just showed you. And so, yeah, this is implicitly assuming that there's sort of, right, we can sort of capture, like, the horizon is long enough that we're going through these cycles enough times. And so once you sort of get into that regime, then this sort of equivalence starts to make sense. And also, as an aside, another important parameter, like you would assume by looking at this instance that maybe an important parameter, if you were trying to generalize this example, would be the length of these sort of cycles. And that can be upper bounded by the span, which is a foreshadowing for later. So yeah, any questions about this example?
I'm not really getting it. What was the significance of this equivalence between estimating for horizon T versus 2T? Like, where are you using that equivalence and for what?
So I guess like I say, I'm trying to argue that the dependence on the horizon should be quadratic and not cubic. And I'm saying that if you believe, sort of as holds for many natural statistical problems, that the dependence on the error is quadratic, then I'm saying you can interchange error and horizon.
Okay, that's kind of, yeah, I agree with that without having this equivalence like argument that's up there, but okay.
Well, I guess, yeah, like it wouldn't necessarily hold if your horizon is too short such that you couldn't reach the end and sort of and make this argument.
Okay. Okay.
So yeah, now I want to talk to you, since we're going to be refining the bounds that achieve a cubic dependence. I wanted to talk to you about those bounds and sort of discuss why they got a cubic dependence and see which steps are not tight for weakly communicating MDPs and how we can improve those steps. So yeah, the result that we're going to be sort of improving for the discounted setting, or that we're going to be looking at for the discounted setting, comes from bounding these 2 terms. So these are 2 different policy evaluation type tasks. So this V hat is the value function with respect to the empirical MDP P hat, which I defined before. So this V hat pi gamma star is the empirical value of the true optimal gamma discounted policy. So we need to evaluate that policy well in the empirical MDP. And then we also need to evaluate well the policy pi hat, which is optimal for the empirical MDP. So if these 2 terms are small, if we evaluate both of these policies well, then we can do sort of the standard following argument using the empirical MDP as sort of a surrogate optimization problem, and we'll be guaranteed that the true value of the Empirical optimal policy is close to, it has a good level of suboptimality. So the following instance-dependent bound is like really key for what we're going to improve. And so yeah, the following instance-dependent bound appears in this paper by Lee et al. And so I guess I want to try and help interpret some of these terms to remind you what's going on here, or yeah, give you interpretation of these terms. So this first term here, I guess each row of this matrix is an unnormalized state visitation distribution, by which I mean that, it gives you sort of a distribution over states that will be visited. If you start in state S, then the S row of this matrix will be a distribution over states which are visited, starting from that state S. But instead of summing to 1, they'll sum to the effective horizon. And then the second term here, I guess I'm calling it the one-step value variance. So this is also, so yeah, this variance parameter here is a vector, and entry S of this vector is the variance in the value function of the next state. So if you start at state S and then you transition to some state S1, what's the variance in the value function of that next state? So yeah, so this is the instance-dependent variance bound that they obtained in this paper, and it's sort of really useful for our later arguments, since we're going to be focusing on getting improved bounds for these variance parameters. So yeah, the next step.
Sorry, excuse me. I have a question about this inequality. So on the left-hand side, I see a scalar, and on the right-hand side, is that a vector or?
Yeah, you're right. Actually, this inequality holds if you didn't have a infinity norm on the left side, and you could also put an infinity norm on the right side. But yeah, you're right that.
Okay.
The dimensions are wrong.
Okay. Fair enough.
Yeah.
Okay.
And then so yeah, the next step here, sort of the standard step here, is to use Jensen's inequality to try to push this sort of unnormalized state distribution on the inside of the square root. And when you do so, since it doesn't normalize to 1, you have to pay this extra factor of square root effective horizon right here. And then here, I guess there's like some algebra, but the main sort of key step in obtaining the optimal sample complexity, at least in the minimax sense, for these discount MDPs, is that there's this law of total variance step, or variance-Bellman equation step, and you can bound this term here, sort of using these interpretations of these terms as a state distribution and a one-step variance contribution. You can relate that. You can bound it by the following term. So this is a vector. Inside of the infinity norm is a vector. So yeah, the entry S of this vector is the variance in the total, in the cumulative discounted return starting from that state S. And so it's clear that this is bounded by effective horizon squared, right? If any state that you start in, your return will be between 0 and effective horizon. So just squaring that. This is where we get this effective horizon cubed dependence in the usual, for sort of the known dependence on horizon cubed. So if we think about, so we actually only need to improve the final inequality of this to get our improved bounds. So we can think about instances where this final inequality is like ignoring constant factors tight. So we can think about an example like the following. So if you start in the state on the left, then you either go up and then you're going to get, reward equal to effective horizon. You're going to collect +1 for all eternity, or you'll go down and you'll collect +0 for all eternity. So this first transition has a huge variance, and this bound is actually tight. This is a Bernoulli multiplied by effective horizon. So this will have large variance. But obviously, this instance is not communicating. So there's some hope that we could just improve this final step. And in fact, you can. And actually, so yeah, as an aside, maybe foreshadowing for later, if I end up having time to discuss the general results, this instance is also not very hard, even though it achieves this inequality. It doesn't achieve some of the other inequalities tightly that I just showed you. And we're going to sort of take advantage of that when we discuss general MDPs. But for now, yeah, let's talk about why we can improve the variance bound. And so, yeah, instead of having instead of having effective horizon squared, we can basically replace this by something like effective horizon times mixing time or time span. And so first is a heuristic argument for why we can replace it with mixing time. So yeah, again, right, we want a better bound for this variance of the total discounted return. So for now, let's just assume, so yeah, this is a rough intuition, but assuming that this policy has a mixing time tau, and also just pretend that this discounted trajectory of horizon 1/1 minus gamma, pretend that it's literally just a trajectory of that horizon, like we actually truncate at that point. So then this longer trajectory of effective horizon length sort of behaves like effective horizon divided by tau independent trajectories, since they mix after tau steps. And so each of these smaller trajectories has a total return itself, which is bounded by tau. And then since they're independent, the variance of the sum of these returns is equal to the sum of the variances. And so we have the sum of this many terms, and the variance of each one of these individual terms is trivially upper bounded by tau squared. So that gives us this improved tau over effective horizon as opposed to effective horizon squared. So yeah, this is a span-based bound, but I guess like the whole goal, or sorry, that was a mixing time-based bound, but the whole goal here is that we want to get the span parameter, which I've argued to you is sort of much better in some cases. So interestingly, like a really similar type of argument, or vaguely similar type of argument works. In particular, like we decompose into segments of length h. And so now I'm assuming that h is an integer. So this can be done by just paying a constant factor. But yeah, I think it's maybe a little mysterious that it works to assume that it's the same length h, but hopefully like the previous example sort of, I guess that's the best intuition I have for why this works. But so we can sort of just use like the tower property and come up with the following multi-step variance Bellman equation. So yeah, if you plugged in h equals 1, you would derive the variance Bellman equation that I'd said was used earlier. But if you sort of expand to multiple steps, you get the following thing. So the variance in the total cumulative return is equal to the variance after h steps. And note that's the variance in the return, but also you have this sort of the variance in the final value function transition. And then yeah, it also depends sort of by the Markov property on the variance in the total return after h steps. And so the reason that you've never, like you might not have seen this before is because it's not useful in general. Because, right, this term, the fact that you have these transitions here, like this value function could generally be order effective horizon. So this term, this middle term would just be bounded by effective horizon, and this wouldn't be useful at all over just trivially bounding the term on the left by effective horizon. But for weakly communicating MDPs, we have something better because we know that whatever state we transition to at time h, its value function will be close to 1/1 minus gamma, which is large, but times rho star, which is state independent. So even though there's sort of a large constant term, right, it's a large constant term which is independent of what state we transition to. So actually the variance contribution of this value function term here is only order h. So that ends up, yeah, letting us improve the bound on this middle term to order h, right? Because we have a sum over h time steps of rewards, which are bounded between 0 and 1. So this middle term will be order h squared. And then sort of if we rearrange, subtract over this term on the right-hand side, we'll get the following bound. So we'll have h squared over 1 minus gamma to the 2h. And yeah, for large enough gamma, you can use Taylor's theorem and show that this is bounded by h over 1 minus gamma, which is what we're aiming for. So yeah, any questions about this sort of key variance bound step?
Yes, I'm still trying to parse through this. So basically you have something on the left-hand side, and then you upper bound it with an expression that has the same thing appearing on the right-hand side, but push forward h times in the transition kernel. And then you reorder this somehow to get the bound.
Well, take sup norm and then you reorder upper bound further, and then reorder.
Exactly, yeah. You can take the sup norm and you can ignore this when you take the sup norm, and you have this gamma to the 2h, which means that this sort of is much smaller than this.
Yeah, right, yeah. So on the left-hand side, you take like the worst state.
Exactly.
And then upper bound the right-hand side with the sup norm. Okay, right. Okay, that's cool. But why is it important to pick h, or like cut things off at h? Maybe this is the part that I did not get.
Yeah, perfectly. I mean, it's a little mysterious, I guess. But I guess, yeah. So one intuition is the derivation I just showed you involving the mixing time. Another intuition is that, well, I guess like if you just look at this bound that I gave you, so it's optimized if you choose h steps, because no matter what we did here, this would be bounded by h. Like if we cut off after 1 step or after 100 steps, we can do the same trick to bound the fluctuations in this term by order h. But then we still have to worry about the sum of these rewards. So if we did any larger than h, then this term would dominate.
Right. Yeah. Okay.
And also, yeah, if we did less than h, so if we just did 1, then we wouldn't have this large. We wouldn't have gamma to the 2h in the denominator. We would just have like gamma in the denominator. Good enough.
Right. Yeah. And the first term would be h anyway, or like h squared.
We would have an h squared in the denominator, the same as here, but then yeah, we would have a 1 minus gamma in the denominator.
Right. Yeah. Okay. Nice. Okay. That's very clear.
So yeah, this basically, yeah, I'm just arguing to you now. Yeah. So right, this big, yeah, variance of in the cumulative return, we replaced, we shaved off effective horizon with an h. So we get the following type of bound, and this bound is like equivalent to the sample complexity that I'm complaining, that I'm claiming. And also, I guess I should say now, I probably should have said earlier, and I probably should have wrote it on the slides also in case anyone just looks at the slides and gets angry. But yeah, so when I'm doing these like less sims, these curly inequalities, I'm ignoring like constants, log factors, and even like lower order statistical terms. So right, Bernstein's inequality, there's another term that you have to worry about. I'm just going to ignore it because it would be too hairy. So anyways, so yeah, this is like, right, one step, like one of these policy evaluation tasks. The second step is to evaluate the empirical optimal pi hat. And so why is this like more work? So I guess if I flip back, right, like we use this key fact here, and this fact here I already showed to you when I was talking about how you can approximate average reward MDPs with discounted MDPs. So if you use this fact here, like this fact applies to the optimal policy pi gamma star, but it doesn't necessarily apply to the empirical optimal policy pi hat. So that's why this is actually like a little bit tricky to get this bound also to work for pi hat, or just a bit trickier. So first of all, it would immediately, if we just replace everything with pi hats, we could immediately use the mixing time assumption. Like if we just wanted to make a uniform mixing time assumption, then we have a uniform mixing time bound and everything would work. But if we want to get it in terms of span, we have to be a little bit careful about how close pi hat is to pi gamma star. And so yeah, there's a sort of recursive error bound step that is involved to sort of solve this problem. And so yeah, as I sort of stated previously, right, like the variance bounds that I just showed you still hold, like these instance-dependent variance bounds, in fact, still hold if you have pi hat instead of pi gamma star. So you can, so yeah, the evaluation error term is bounded again by this variance parameter. But yeah, right, this is a different variance parameter than before. But still, you can recursively bound this variance parameter in terms of the evaluation error. So if we do the same multi-step variance Bellman equation as before, so if we look at this middle term, which we want it to be bounded by order h squared like before, right? So since we know that the variance bound holds if you have a v pi gamma star as opposed to a v hat inside of here. So we can get something like h squared plus the difference between those two. And then basically because of that argument that I showed you before about sort of why this problem reduces to evaluating those two policies, or the fact that sort of we're choosing pi hat to be optimal for the empirical MDP, we can bound this term by order h squared plus the evaluation error for pi hat. And that's only if we're already evaluating pi gamma star to order h. So I think I'll pause here, and this might be a bit confusing, or I'll let you think about the last step.
Yeah. This inequality, I'm not sure I'm getting it. Or maybe I missed your earlier argument as to why you can replace that v pi gamma star with the v hat pi hat.
Yeah,
without a constant factor somewhere.
So you do pay not a constant factor, but an additive h squared. But I have a big O, so it doesn't matter.
Okay, so you have like a 2h squared, let's say.
Yeah, exactly. So yeah, this term right here is exactly your suboptimality of pi hat. And I said, right, bounding the suboptimality of pi hat reduces to bounding the evaluation error on pi hat and the evaluation error on pi gamma star. So if we're already evaluating pi gamma star well to order h, then we can also then we can just reduce this to h squared plus this remaining evaluation term.
Right. Okay. Yeah. Got it. Yeah.
And so yeah, I guess this is just a bit tricky because when you have the span, like you want to get an instance dependent bound, and that depends on the optimal policy in your MDP, but you have to worry about the variance parameters of suboptimal policies. So that's why I'm sort of highlighting this step. Is sort of it's sort of a fundamental thing that you'll have to run into.
Just kind of very luckily everything traces back to just evaluating accurately the optimal policy in the discounted MDP, which you already have. Like you were arguing that, I mean, like it's not too accurate. Like that's the other thing. Like that doesn't have to be too accurate. Just up to order h.
Exactly. Yeah. But I do think that it would break down if you didn't have order h.
Yeah. So that's how you're breaking out from this seemingly kind of self-biting thing that, like, okay, you want to argue about pi hat, that pi hat is close to pi gamma star in terms of its value, and for that you need to, like, you end up here seemingly comparing the same thing, and then okay, but no, you don't actually need the same accuracy. You need a much worse accuracy here.
Exactly. Yeah.
Or it's sufficient. Yeah. Good.
Cool. So yeah, that's, I guess, the last of my results for discount MDPs. I guess I'm not sure how much time I have.
Yeah, I was gonna point out that you should probably try to wrap up in like 5 minutes if possible. So maybe just presenting the motivation results and not the proof sketch or something like that.
Yeah, that sounds great. And maybe we can talk about the proof sketches sort of in informal Q&A. Since and they're very brief anyways. But yeah, so I quickly want to just talk about sort of general MDPs. So it's obviously impossible to achieve sublinear regret in general MDPs if you have like an online setting, right? Because obviously you could have an example like the one I showed you before. So it's sort of like the one I showed you before, but now there are two actions. So if you go up, you'll be happy. If you go down, you'll regret it forever. So it's obviously impossible to achieve sublinear regret for general MDPs, which are not weakly communicating. However, there's no such obstacle for the simulator setting. So we can ask, can we still, get bounds for the simulator setting? And also, yeah, does the sample complexity of general MDPs, how does it compare to that for weakly communicating MDPs? Like, are they governed by the same complexity parameters? And so the finding is that no, they're not governed by the span of the optimal policy alone. So let me walk you through this example here. So yeah, we have the key state is state 1 here. So if you're in state 1, okay, yeah, you can see my cursor. So if you're in state 1, you have two options. You can either take action 2, which goes up, and then yeah, you'll collect 0.5 reward, and then you'll be trapped in state 2 forever, where you'll be collecting reward 0.5. Alternatively, you could take the down action, or action 1 from state 1, and then two things could happen. With a high probability, you'll end up back at state 1, and when you do this, you collect a reward of +1. So that looks very good. However, yeah, you have a small chance of getting trapped in state 3, where you collect reward 0 for eternity. So in a short-term setting, you might want to gamble. In a short-term setting, you do want to gamble and take action 1, because there's only a small chance that you'll be trapped in the bad state. So you should go down and yeah, try your luck there. But for the long-term reward setting, for the average reward setting, you would never want to take such a risk. You would only ever go, because deterministically, I guess I should say, yeah, almost surely you'll end up in state 3 if you take the down action. You'll always end up there, so you should never take the down action. You should, your optimal policy will be taking the up action. However, discounted MDPs, the discounted approximation, doesn't capture this. So I guess we should compute the span of the optimal policy for this instance. So like I just said, the span for the optimal policy is just going up. And so because the span of the policy is just going up, it doesn't matter what's going on for this down action. We don't have to worry about the span of that policy. And that's sort of the reason why this can't just depend on the span of H star. So the span of H star, if you go up, you collect reward 0.5, and then your average reward is 0.5. Then also once you're in state 2, obviously the span from there is 0 as well. So the optimal policy of going up has 0 span. However, you need to correctly rule out the bottom policy, and you're not going to do that for a small horizon. So the gamma discounted approximation fails unless the effective horizon is sort of much larger than the span of the optimal policy. The second thing is that even if you had full knowledge of this MDP, the approximation result wouldn't hold. So you couldn't even plan in such an MDP if you were using a discounted solver, unless you used a much larger effective horizon for your solver than just based on the span. But if you're also looking at this from a statistical perspective, you don't observe these these transitions which make the down action bad. You don't observe them very frequently, You need at least T samples before you observe one. So statistically, your complexity can't be independent of T, because you need to observe such an example, or otherwise you're going to think that if I take the down action, I just stay in state 1 forever and collect +1 reward. So this sort of shows some sort of approximation and statistical hardness. The statistical hardness is obviously not capturing the right dependence on epsilon and S and A, and we have a lower bound which does take care of those things. And so yes, yeah, the last thing I want to say about this is just that, so we come up with a parameter called bounded transient time, which is satisfied with value B if the expected amount of time spent in transient states under any policy is bounded by B. So here B is equal to this T. So the expected amount of time that we would stay in the transient state 1 if we took the down action is B. And so we also need to depend on that parameter. And we can sort of do the exact same things that we did before, but instead now we'll take in our reduction to discount MDPs, we'll use an effective horizon which looks like span plus B instead of just span, and that will give us the following complexity for average reward for the average reward setting, and that is again a corollary of a result for the discounted setting, where again, we have a quadratic dependence on the horizon, on the effective horizon, but now we have a B plus H instead of just an H. And yeah, we also have a lower bound, which captures the right complexity. And I'll skip over these brief proof sketches. And so yeah, I just want to end with a few takeaways and questions. So as we saw, if we sort of fix the MDP and we vary only the gamma, sort of treating it like it sometimes is used in practice as more of a tuning parameter, then actually in both settings, even for general MDPs, we get a sample complexity which is only quadratic in the horizon. And instead there are these sort of other complexity parameters which sort of shave off a factor of the effective horizon. And maybe the effective horizon is too low, we can actually truncate even further, but sort of in a long gamma setting, the dependence on the effective horizon is quadratic. And so yeah, we approve this horizon dependence crucially by bounding certain variance parameters in terms of the average reward complexity parameters, H and B. And then I guess I didn't talk about this, but yeah, there is sort of a key role played by transient states for general MDPs, which interestingly is not the case for weakly communicating MDPs. So in particular, like the general complexity that I showed you here doesn't simply reduce to the weakly communicating complexity. And so I guess, yeah, this is a sort of interesting question to try to unite these two settings. And yeah, that's all. And thanks for listening.
Yeah, thank you. Beautiful. Yeah. This is very exciting work. So maybe I can just remind people that they can raise their hands or pose their questions in the chat, and then we can continue talking. So I certainly have a bunch of questions. So the first one is sort of like a high-level one regarding your proof strategy, which I'm not sure I got entirely right because there are like so many moving parts in this analysis. So is it that you solve a discounted MDP with like a very long horizon that depends on epsilon, and then just plug in the result of that method into a low precision algorithm? So is that what you do, or is it that you just set a gamma which is of the order 1/1 minus h or something like
that? Yeah, no, the effective horizon also depends on epsilon.
Right.
So yeah, for this sort of, I guess, yeah. So I just flip back to the slide where I show the. All right, and so this is in prior work, and I guess we also have an analog of this for the general setting in our paper. But yeah, so this is from prior work, and this is the how to reduce to discount MDPs. So yeah, to make this term here less than epsilon, yeah, you need to have your 1 minus gamma is 1 over the effective horizon, and you need that to depend on epsilon. So the idea is that you solve, like, you don't need a great solution to the MDP. And I guess for this thing I've been telling you about, like, if you have a long horizon, then that sort of alleviates the need to solve to a low accuracy. I guess is one way of saying it. Like, you can trade off horizon and accuracy for this regime. And so, yeah.
Yeah, right. So it's basically still based on the same type of decomposition, and it's still using like a very long effective horizon, let's say. So maybe that's a bit of an open-ended question, because but I always felt that it should be possible to just set like a large gamma that is like a little bit larger than h, or like that induces a horizon that's a little bit larger than h, let's say like h log 1 over epsilon or something like that, and then just solve for that. Like, do you think that would be like a plausible proof strategy, or that's just hopeless?
I guess I've been working on something that's a little similar to that, and I think that might be possible, but I think that you might have issues with. I wonder if that could work in the finite horizon setting, basically. But I think that you might have issues in the discounted setting. You might sort of mess things up with just the fact that you're discounting would probably mess things up. You need a really small discount factor.
So by the finite horizon setting, you mean that there is some horizon after which everything restarts and you go back to the initial state? and here you basically can ignore everything after a large enough effective horizon, or
I guess I mean that, yeah, if you don't use a discounted approximation, but instead you solve like a certain finite horizon MDP, and then it just terminates at a certain time.
Yeah,
it might be possible to sort of do something like you're saying, but I don't think that it's. I guess I'm not exactly. I guess I don't want to claim that you could. I mean, okay, let's say you could do so. Like, I think that would, like, if you could do so perfectly, I think that would probably like give you a better sample complexity than the bounds that I'm saying are optimal. But like, I think that you can do something in AMDPs without taking the horizon to be like 1/epsilon.
Yeah. Because my feeling is that at least there's this black hole discount factor on after which the optimal policy does not change. So intuitively, if I set my discount factor to be larger than that, right, I'm sort of solving the right problem, and I should not be messing things up all that bad.
Yeah.
Well, I guess maybe this is like way too open-ended of a question to be discussed at this very moment. Maybe Csaba can ask his questions.
Well, just on this black hole optimality, doesn't it depend very, like in a finicky way, on the parameters of the MDP, like the critical threshold? It's like, yeah. So I don't know whether that sort of is a way out, because it's not true, right, that the critical parameter for the discount only depends on the span. It depends on
certainly not true, right? It's
something more complicated, right? Yeah.
It's another complicated problem.
So because of that, I don't know whether this intuition that you can use black hole optimality is going to hold. Like, it brings in other properties of the MDP.
Yeah. No, I'm not talking about like developing like a practical algorithm here. I'm just thinking about like putting together like a proof strategy in the first place that relies on this argument.
But I sort of feel that maybe that's troublesome too. Anyways, a related question to this is this practical? I mean, we don't know age, right? So what do we do? Actually,
yeah. So I guess maybe in some practical setting, age. I guess if you
most likely.
I think in general it'd be hard to estimate age. I guess I'm not sure how you would do that, but I think what you could always do is replace h with an upper bound. So you could replace it with diameter or the mixing time, which you could estimate.
I guess I'm asking a question: can we adapt to age so that if we don't know age, so is this a sample complexity bound that says that your sample complexity is such and such if you know age, or is it a sample complexity bound that says that no matter what age is, your sample complexity is such and such, and okay, here's how you do it? I guess for now it's the first kind, so it's not adapting to age. And then there is the question whether there is a real price to adapt to age. Yeah.
Yeah, I mean, currently you need to know age.
Okay.
Our conjecture is that there is another algorithm that does not need to know age, but we're still working on it.
Okay, cool. Very cool. Yeah. Yeah, that would be really awesome to have. Gerge, there is a question in the chat.
Oh yeah, so you can. The question is, can we estimate mixing time instead, or is there any issue to doing that? Yeah, you could estimate the mixing time instead, but that would be inferior to the span-based bound.
Yeah, but that would be just as hard as estimating the span, because it would need to be a bound on the mixing time of all policies, I suppose, including the optimal policy. And for that, you would need to.
We don't know what the optimal policy is. Yeah.
Right. Yeah.
It's not necessarily simple. And also mixing time estimation is, yeah, like for these general Markov chains is not a panacea. Far from it. Yeah, Arya has some good work on that. But yeah.
Maybe I'll stop the recording here.